Hello, everybody. This is a data mining insurance case study for Management 645. My name is Ryan Clark, and with me I have Brandon Blair, Robert Boone, and Gavin Jones. If you go to the next slide. So the purpose of this case study is to analyze and mine the data from a bank to help predict customers that are more likely to purchase insurance from the bank. And to find out and make this prediction, we did a variety of methods to analyze it, including decision trees, regression, and neural networking. And the reason that this information is valuable to the bank is that being able to more accurately predict which customer's demographic will purchase the insurance based on the different types of analysis we'll be doing, the bank can decide how to adjust their tactics for selling the insurance, who to target, where to target, and just overall have more success in their efforts with selling the insurance product. You go to the next slide. So we have 50 variables with 19,357 observations available to us, and some of the variables are binary, which is yes and no, while others are numerical. And whenever you combine these two types of data, you can get a pretty accurate prediction rate of which customers in the end will purchase insurance. And for the process of predicting the customers that are more likely to purchase it, we can narrow down which variables to analyze based on the importance of them. And we can focus on them more, and we can combine a variety of them with different methods to get an even better idea of which customers will purchase the insurance. We go to the next slide. So the top graph here is a chi-square plot. And this plot displays the importance of each categorical variable in predicting the target. And we do this by looking at the stat explore node, and we can analyze different aspects of the variables. For the chi-square plot, the top three categorical variables are whether the customer has a certificate of deposit, has a checking account, or has a money market. So this is a yes/no option or binary. For the bottom chart there, that is a variable importance plot, and that displays the most important numerical variable in predicting the target. So the most three important numerical variables based on that chart is the balance in the customer savings account, balance in their checking account, and the certificate of deposit balance they have. So the above variables I gave are the most important, which means that they are the biggest factor in predicting whether or not the customer will purchase insurance. So knowing each one of those can give a pretty good indication of if they fit the demographic of someone that will purchase the insurance. And with that, I will pass it off to Gavin, and he'll tell y'all about skewness and kurtosis.
Variable skewness and kurtosis. This is where we determined if a transformation process was needed for our given variables. Each of the variables through exploration ended containing a significantly high kurtosis and skewness. The variables graphs were also heavily skewed to the right. The example to the right here shows the credit balance having a high skewness at 11.2 and a high kurtosis at 204. Lastly, multiple variables, including the more important variables that we identified before, were missing at least 1,750 values. With this, we determined that the process of transformation and imputation were necessary. For the transformation, we established the skewness range of good variables between -2 to 4, which means that they do not need to be transformed. The minimum columns in the graph had to be at least 4, and the transformation type was set to log. Overall, 19 variables fit the criteria to be transformed within the transformation process. To the right, we see the same graph after the transformation with a significantly improved skewness and kurtosis. For those missing values, the certain criteria were set to where the cutoff was at 50%. The class variable input method was then set to count, while the interval variable was set to mean, and the indicator variable type was set to unique to identify each distinct value type. And now I'm going to hand it off back to Ryan.
Awesome. So after we analyzed the different variables, figured out different things about them relating to their kurtosis and skewness, we started doing our analysis models. And for the first model, we did decision trees. And to find out the best one that suited our needs, we built a few different trees. We compared multiple different ones, and this subtree assessment method gave us the best results. And for the method, we set it to assessment, and the assessment measure is set to misclassification. And the reason that we did that is it leads to the lowest level of misclassification and a low level of overfitting. And with a lower level of misclassification, it'll more accurately predict whether the customer will purchase insurance or not. If you go to the next slide. So once we ran that tree, this was the result that it gave, and the final tree results in 16 leaves, and it has a misclassification rate of 0.259 rounded for training data and 0.257 rounded for validation data. And overall, this is pretty good because it shows that it predicts whether or not the customer will purchase insurance correctly, roughly 74% of the time. If you go to the next slide. And as you can see here, the subtree assessment plot shows a misclassification rate as the number of leaves increases. So as you go to the right, that's the more leaves there are, and the vertical axis is the misclassification rate. You can see that based on this, that vertical blue line is where it selected the final model, which is at 16 leaves. So that's where it decided that it had the lowest level of misclassification and therefore the best model for our needs. And you'll see that there is some divergence going on there, but it's not bad enough to have overfitting as much of a concern. So overall, it fits pretty well. If you go to the next slide. This is the variable importance table, and it displays exactly what it sounds like, the importance of each variable in descending order. You can see that the most important variable for predicting the target is the savings balance. And this decision is whether or not, or whether the customer is greater than or less than $8,721.91 in their savings account. This means that the most important deciding factor in the end for whether or not the customer will purchase insurance is that amount, if they have more or less than that in their savings account. The second most important variable on the decision tree is whether the customer has a money market account or not. So this isn't a balance amount, it's not a numerical amount, it's a binary. So do they have a money market account or do they not? And then third is the balance of the checking account. So this ties in with the savings balance. It's a numerical value if they have greater than or less than a set amount. So each one of these variables play a pretty big role in accurately predicting the target on their own, but whenever you take them all into consideration, you can get a more and more accurate prediction of whether or not the customer will purchase insurance. If you go to the next slide. So this is a cumulative lift chart, and as you can see, the validation data at the 10th percentile is 2.007 for validation and 2.158 for training. And this indicates that in the top 10% of cases for validation, it is roughly 100% more likely to have predicted the outcome than if there had been a random selection of 10% of the cases. And for training data, the top 10% of the cases are roughly 116% more likely to have predicted the outcome than if there had been a random selection of 10% of the cases. And with that, I will hand it off to Gavin and he'll tell y'all some about regression.
For the regression analysis, a stepwise regression model was chosen due to the methodology providing a regression model that is stable while providing the most accurate results. The current configuration of our stepwise regression model has an entry of 1 to include all input variables to be considered, and a state of 0.5 so that more variables will be left in the final selection. Lastly, the number of steps was set to 30 and the selection criteria is set to validation error since the purpose is to estimate and make a decision for the final output. These are our important variables. This is a list of them. And these were found when performing an analysis on the odds ratio point estimate with their interpretations. The savings variable was the most important variable considering that a person was 5.87 times more likely to purchase insurance when they had an open savings account. The second is a checking account, where an individual is about 3.4 times more likely to purchase insurance. And a line of credit was also significant, which was at 1.8 times more likely to purchase insurance. One thing to note is that branch 19 is the likeliest to sell insurance amongst the rest of the branches. Here are the results from the regression model. Once completing the regression model, we were able to look at the fit statistics and determine how effective the stepwise regression was. The validation ASE was low at 0.177349, and the train ASE was 0.172037. The validation misclassification rate was at 0.2663, and the training misclassification rate was at 0.2572. This insinuates that the difference between the train and the validation level for the misclassification rate was low at 0.009069, which meant that overfitting was not an issue. Okay, and lastly, here is the cumulative lift chart. The top 20% of customers were evaluated. The stepwise regression model did 96% better than the baseline when pertaining to the validation, and the model performed 101% better than the baseline on the training. And now I will be passing it off.
Cool. Thanks, Gavin. So my name is Brandon Blair, and I'll be going over our first neural network model. So as you can see from this slide, this is how we initially configured our neural network model. Multiple different types of configurations were tested, but this one provided us with the most stable model and the least amount of overfitting. With this first network model, we first connected it directly to our imputation node. And by doing so, it allowed us to avoid repeating any transformation or missing imputation of the variables. Next, we tested the maximum number of iterations the model would need to successfully converge. At first, we started off with 100 iterations and discovered that the model only needed 70 to successfully converge. So we set the minimum number of iterations to 70 for better optimization within the model. We then began performing tests on the number of missing values and discovered that the default value of 3 provided the model with the least amount of overfitting. Any deviation from this number resulted in various amounts of overfitting. We also discovered that disabling preliminary training helped with any overfitting. Next slide, please. Here we can see the results of our first neural network model. Again, we can see that the model converged at 70 iterations. However, the best model was chosen at the 19th iteration. This model also resulted in fairly low average square error values and misclassification rates, meaning that overfitting was not a major concern. Next slide, please. Lastly, we compared this neural network model to our cumulative lift chart. Essentially, we evaluated this model where the depth is equal to 10 on the cumulative lift chart. And as you can see, our model did approximately 112% better than the baseline when looking at the validation line in red, and approximately 118% better when looking at the training line in blue. What this means is that the performance of this particular neural network model is roughly 2.123 and 2.189 times better than that of the baseline model for the top 10% of customers, respectively. Next, I'll hand it off to Robert. He's going to go over our second neural network model.
Thank you, Brandon. Yeah, so I did the neural network model following a logistic regression model. So we attached it to the end of the logistic regression model, and we decided to configure it as follows. There was a maximum number of iterations was 145. After playing with that quite a bit, we found that that seemed to give us the best numbers on the output. Hidden units were 10. Model selection criterion was misclassification, and we disabled the preliminary training. Next slide. So after running the node with those configurations, the model converged at 144 iterations. The validation average square error came in at 0.175, and the validation misclassification rate came out to approximately 0.255. Training ASE was 0.16, training misclassification rate was 0.235, and overfitting did not appear to be much of an issue. That's because the difference approximately was negative 0.020535, meaning that it did not appear to give us any trouble there. Next slide. So when compared to the baseline performance model at the 10th percentile, this model did approximately 2.14 times, or around 142% better than that of the baseline model regarding cumulative lift on the validate line. As for the train line, our model did 2.36 times, or around 360% better than the baseline model. What this means is that the performance of the neural network is 2.142 and 2.36 times that of the baseline model for the top 10% of customers. Next slide. Oh, I'm handing off to Brandon here, actually.
Thanks, Robert. So now in order to determine which predictive model was the best out of all of them, and this is in terms of ROC index, average square error, and misclassification rate, we decided to implement a model comparison node at the end of our diagram. With this node, we were able to graph the ROC index of each given model and compare it to a baseline within the graph. With this node, we could also evaluate which model had the lowest average square error and misclassification value from the output window. Our overall conclusion after running the node was that the best predictive model out of the bunch was our second neural network. This was the selected model within the comparison node, and we can see from the output window table on the right that it had the lowest ASE and misclassification rates compared to the other models. To further justify why it was chosen, we can also see that it deviates furthest from the baseline on the ROC index table, meaning that its area under the curve value, or AUC value, was closest to 1, meaning it is an excellent qualifier for predictive analysis when compared to our other models. And now to wrap things up, I'll hand it back to Robert.
Thank you, Brandon. So in conclusion, we suggest that the bank use the neural network following the logistic regression, because as Brandon just explained, it gave the most accurate prediction of which customers will purchase insurance. Now, for our analysis, we're suggesting that clients who are most likely to purchase insurance, they kind of seem to be on the wealthier side. The variables that seem to correlate the most with people who would purchase insurance had a higher savings balance, more investments in their portfolios, and a lower credit card debt balances. With this said, we think that an interesting way that the bank could go about increasing their insurance customer base is to actually target the lower income insurance market. Since there's not a lot of people in that area, in that demographic, that are purchasing insurance, it means it's a much larger untapped market. And we think that the bank could tailor a product and an ad campaign for this demographic and potentially bring in a significant amount of customers. Ways that they could do this might be to include a savings account whenever they decide to sign up for insurance. Maybe include a optional class on money management that helps educate these potential customers on the importance of financial security and how that is achieved. This could have a twofold benefit to the bank by not only increasing their revenues, but it could also help the local economy while benefiting the bank's reputation within it. Additionally, we also highly recommend that the bank attempt to maintain a stronghold in the higher income market by continuing to offer traditional insurance products and services to current and future high dollar future bank customers. And next slide. With that, we say thank you, and that's our presentation.
Thank you.